Dear physics aspirants, right now I have the topic motion in a straight line. And here acceleration will be the subtopic. Acceleration will provide you the understanding of the subject matter. Here you will see the acceleration, the velocity of an object in general changes during its course of motion. How to describe this change should be described as the rate of change in velocity with distance or with time. This was a problem even in Galileo's time. It was first thought that this change could be described by the rate of change of velocity with the distance. But through his studies of motion of freely falling objects and motion of objects on an inclined plane, Galileo concluded that the rate of change of velocity with time is a constant of motion for all objects in free or free fall. On the other hand, the change in velocity with distance is not constant. It decreases with increasing distance of fall. This led to the concept of acceleration as the rate of change of velocity with time. The average acceleration a race over a time interval is defined as the change of velocity divided by the time interval. A dash is equal to v2 minus v1, t2 minus t1 is equal to v by t is equal, it is known as 3.4 here, and where v2 and v1 is the instantaneous velocity t's, or simply velocities of time t2 and t1. It is the average change of velocity per unit time. The SI unit of acceleration is meter per second square. On a plot of velocity versus time, the average acceleration is the slope of the straight line connecting the process corresponding to v2 and vt2 and v1 and t1. The average acceleration for velocity time graph shown in figure 3.7 here. Graph is here. Different time intervals: 0 second to 10 seconds, 10 seconds to 18 seconds, and 18 seconds to 20 seconds, and 0 seconds to 8 seconds acceleration. It's same here, 10 second to 18 seconds you will see here. And figure 3.8, acceleration as a function of time for motion, represented in figure 3.3. Figure 3.3 here you will see. Instantaneous acceleration is defined in the same way as instantaneous velocity. Acceleration limit t tend to 0, v by t dv by dt. The acceleration at an instant is the slope of the tangent of the vt curve at the instant. For vt curve shown in figure 3.7, we can obtain acceleration at every instant of time. The resulting acceleration minus t curve is shown in figure 3.8. We see that the acceleration is non-uniform over the period 0 second to 10 second. It is 0 between 10 second to 18 second and is constant with value 12 meter per second between the 18 second to 20 second. When acceleration is uniform, obviously it equals to average acceleration for over the period. Since velocity is a quantity having both magnitude and directions, the change in velocity may involve either or both of these factors. Accelerations therefore may result from a change in speed magnitude, a change in direction, or changes in both. Like velocity, acceleration can also be positive, negative, or zero. Position time graphs of motion with the positive, negative, and zero accelerations and so on. Figure 3.9 you will see here, and respectively B also. Now note that the graph curves upward for positive acceleration, downward and negative accelerations, and a straight line for the zero acceleration. When exercise, identify the frequency and regions of the curve that just correspond to these three cases, although acceleration can vary with the time. Our study in this chapter will be restricted to motion with constant acceleration. In this case, the average acceleration equals to the constant value of the acceleration during the intervals. If the velocity of the object v is equal to t is equal to 0 and vt, we have position time graph and motion with the positive accelerations magnitude and acceleration and zero acceleration. So let us see how velocity time graph looks like for some simple cases 3.10 so on. You will see here. And now velocity time graph looks some simple cases 3.10 so velocity times with a constant acceleration for the time following cases. An object is moving in a position directions with the positive acceleration. For example, the motion of the car in figure 0.3 between t0 second to t10 seconds. An object of the moving positive directions with the negative accelerations. For example, motion of the car 3.10 between t18 second 20 second. An object of the moving negative directions with the negative acceleration. For example, the motion of the moving of O in figure 3.1 negative acceleration with increased speed. An object is moving in positive directions till time t and then turns back with the same negative acceleration. For example, motion of a car O point in figure 3.1 till t to the decreasing speed and back moving with the same negative acceleration. You will see here x-axis origin 3.1 positions of the car in different times. And interesting features of the velocity time graph for any moving object, the area under the curve represents the displacement over a given time interval. Here you will see. And here the statement requires of use of calculus. Calculus will be needed. You will see here the details 3.10 and WC can however see that it is true for the simple cases and object moving with the constant velocity u. Its velocity time graph is shown in figure 3.811 and here area under VT curve equal to displacement of object over a given time interval. The VT curve is a straight line parallel to the axis and area under it between t0 t is the area of the rectangle of height of u. Here a rectangle rule u and t, therefore area ut is equal to ut, which is the displacement of the time intervals. How come in this case an area is equal to the distance? Think, note the dimensions of quantities and two coordinate axes. You will arrive at the answer. Note that the x, t, vt and at graphs shown in several figures in this chapter have sharp kinks at some points, implying that some functions are not differentiable at these points. In any case, realistic situation, the functions will be differentiable to all points and the graphs will be smooth. What this means physically is that acceleration and velocity cannot change. We'll use it abruptly at an instant. Changes are always continuous. So thank you. We will meet in next video. Kinematics equations for uniformly accelerated motion. Thank you.